modulo 2 pi, then having a theta term equal to pi is consistent with time reversal symmetry. Okay, and so this is this idea that in a topological insulator you have a theta equals pi. Okay, so in a sense, this this is kind of like the story that I told you about the electric polarization in one dimension. So remember, in one dimension we had this this quantity which is the electric polarization, and it was uncertain because I could always add an electron to the end. Okay, so the fractional part of the electric polarization was meaningful, but it was only defined modulo E. And likewise, the Berry phase, going around the Brillouin zone, the fractional part of that was all well defined, but if I do a large gauge transformation, I can change it by an integer. So these two sort of have the same ambiguity. So the story is the same for this theta term. So if I think about the magnetoelectric polarizability, then the part that is determined by the bulk is only the fractional part of this. It's this 1/2. I could always add, just by adding an extra quantum Hall layer on the surface, I could change this by E squared over H. And now it turns out it's possible to determine what this theta term is in terms of the Bloch band structure, and I'm not going to explain how to derive this formula, but what this formula is it's sort of a three-dimensional generalization of this, and so this is called a Chern-Simons form, and so this is a quantity which again is gauge invariant under small gauge transformations, but if you do a large gauge transformation, this can change by an integer. And so it has the same property that that it has this intrinsic ambiguity. It's only the fractional part of it that is meaningful. Yes.
Do you need the trace there?
Do I need the trace? Yeah. So I'm viewing this A now as a matrix. So if I have Bloch states, then I have, A is Ui d by dk Uj. So it's a matrix.
You're talking about degenerate.
Huh?
Degenerate ground state, since it's a matrix.
No. I have many bands. Okay. Yeah. And so in general, so I have to use the fact that this connection is actually not a U1 connection. It's actually, there are more states.
No, yeah. The Berry connection is typically defined with respect to a single eigenstate or an eigensubspace. So what do you?
Well, now I have several of them. So I have several bands now. So I have a UN. I have several bands, and I can imagine rotating by a UN transformation among those bands. That doesn't, if I have n occupied bands, if I do a UN transformation among those bands, that doesn't change the many-body ground state.
I see. So you're only considering not necessarily all the states, but a finite number of such states.
Yes.
You're looking at the connection.
Yeah, the finite number of say occupied states.
Okay.
Yeah.
Because if you considered all of them, it would be a trivial connection.
I agree, but I'm only considering the occupied ones. Yeah. Okay. All right. Okay. So so when you break time reversal symmetry on the surface, we're still doing non-interacting electrons. So in the case it's trivial, but it's there's some interesting subtleties associated with that. So now what I want to talk about is I'm going to stop talking about topological insulators for a little bit, and I want to introduce the idea of topological superconductivity. And in order to introduce topological superconductivity, let me just say a few words about superconductivity. Okay, and so so here I think we have we have different backgrounds that you have. And so for the condensed matter theorists, we learn about semiconductors first, and then we learn about superconductors, and then we learn about Majorana fermions. Okay, and so for me, you know, I was able to understand a superconductor by thinking of it as being like an insulator. And then that allowed me to finally understand what Majorana fermions are about. Okay, whereas for those of you with a high energy background, the first thing you learn about is Majorana fermions, and then maybe you learn about superconductors, and then maybe you learn about semiconductors. And then you say, well, I finally understand what a superconductor is because it's just Majorana fermions. So I'm going to give you my perspective on this, which is to think about a superconductivity. So what you do in a superconductor, so basically the magic is that in mean field theory, the mean field description of a superconductor is a theory of non-interacting fermions. Okay, but the price that you pay is that so when you do this mean field theory is that you have so your Hamiltonian is quadratic in the fermion operator, so it's a free fermion theory, but it has these anomalous terms which with two creation operators or two annihilation operators. Okay, and so in order to describe this, then what one usually does is to write the Hamiltonian, write the many-body Hamiltonian as a matrix like this, where both on the left and on the right I have both psi and psi dagger. Okay, and so now, so then when I do that, I can write a Hamiltonian that involves these anomalous terms, and the anomalous terms sort of give me the off-diagonal components of this matrix. Okay. Now, when I've done this, though, I've done something drastic because I've made two copies of my original problem. Okay, and so so by making these two copies of the original problem, what I'm able to do is I'm able to turn this sort of non-trivial superconducting problem into a problem that looks like an insulator. Okay, so again, so now I have this Hamiltonian, and in a superconductor there's an energy gap. Okay, which it has a conduction band and a valence band, just like an ordinary band structure that I've been talking about all along. But the price that I paid is I made this artificial doubling, and so by making this artificial doubling, I have introduced an intrinsic symmetry that this Hamiltonian has to obey, and so it has to obey sort of an intrinsic particle hole symmetry. So remember when I talked about the Sushri-Verheugen model, I said there was some artificial symmetry that it has that guarantees that the conduction band is a mirror image of the valence band. So this now is a real intrinsic symmetry, and in fact it's a symmetry actually that kind of looks like time reversal symmetry. So my Hamiltonian anti-commutes with this operator, but this operator is an anti-unitary operator, which sort of is like time reversal symmetry. Okay, and so this Bogolubov-de Gennes Hamiltonian is like the Hamiltonian of a insulator, if you will, but it has this intrinsic symmetry, and moreover, in addition to having this intrinsic symmetry, again, the conduction band looks just like the valence band, but in fact, the conduction band and the valence band are redundant with each other. Okay, which means that I can consider two different, in an insulator, I can consider two different excitations. I can imagine adding an electron into the conduction band, or I can imagine removing an electron from the valence band. Okay, and in an insulator, those are two different states. Okay, in fact, they have different numbers of particles. Okay, but in a superconductor, these are actually the same state, and the reason so the reason they look different is because we introduced this artificial doubling. Okay, and so one has to keep in mind and the reason these can be the same, of course, is because you can give Cooper pairs away to the condensate for free. Okay, and so the number of Cooper pairs is not definite in a superconductor, and so that's how these two can be actually the same state. Okay, and so we have to keep this redundancy in mind, that adding a particle into the conduction band is the same thing as removing a particle from the valence band. Now, so now we can. So now that we've turned this problem of superconductivity into a problem that looks like an insulator, then that poses the natural question: could there be topological classes of superconductors? Okay, and so now, though, what we have is we have to impose a different symmetry. So remember, when we imposed time reversal symmetry, we got some extra topological structure, which was different than what we had when we didn't have time reversal symmetry. So now we have to think about what happens if we impose this this intrinsic particle hole symmetry. Can that give us any different topological classes? Okay, and so the answer, of course, is yes. You can have topological superconductors, and the simplest version of this is thinking about one dimension. Okay, and so in order to sort of understand this in the most simple way, what I want to do is I want to do what I've been doing all along, which is to first think about the boundary and ask, well, what kinds of protected things can I have on the boundary? So the boundary of a one-dimensional system is, of course, the zero-dimensional end. Okay, and so if I have a superconductor with an energy gap, then it's always possible that I could have states which are, inside the energy gap, and these states are then localized. They're sort of exponentially localized at the end. Okay, and so depending on what the Hamiltonian at the end is, you might have these end states. But the thing is that because of this intrinsic particle hole symmetry, is that if you have a state at energy E, then it has to have a partner at energy minus E. Okay, unless you had a state that was at exactly zero energy. Okay, and so this zero energy state would be its own partner. Okay, this doesn't break the rules. This still has the particle hole symmetry. But what you can tell is that if you have this state exactly at zero, then you can't get rid of it, because if you tried to move it away from zero, then its partner would have to appear out of nowhere. Okay, and so that can't happen continuously, and so this zero mode is topologically protected, in the same way that the chiral edge state of the integer quantum Hall effect is topologically protected. You can't get rid of it by doing a smooth deformation. The only way you could get rid of it is by making this bulk gap close down to zero, and then you could get rid of it. Okay, and so now, of course, what is it that determines whether or not you have this zero mode at the end? Well, it's whether or not the one-dimensional superconductor is a topological superconductor or not. Okay, so now, of course, this zero mode is sort of a magical thing, because I told you that we have this intrinsic redundancy that we've imposed in our states, and so adding a particle at energy E is the same thing as removing a particle at energy minus E. Well, that means that adding a particle at energy zero is the same thing as removing a particle at energy zero. So that means that adding a particle into this state does exactly the same thing as removing a particle, so it's like the particle is its own antiparticle. Okay, and so this is the defining feature of a Majorana fermion. And as Shivaji explained yesterday, we can think about this Majorana fermion as being like the real part of an ordinary Dirac fermion, which can either be occupied or empty. Okay, and so two of these Majorana modes defines a single Dirac fermion. Okay, and so for instance, if you have a one-dimensional topological superconductor, you're going to have a zero mode at both ends, and those zero modes define a single Dirac fermion, which defines two states. Okay, and And so this is a interesting situation where so of course if your one-dimensional system is very, very, very long, if it's effectively infinitely long, then this zero mode is protected. If it's finite, then the zero modes that you have at each end will couple to each other, okay, just like in what Shivaji was describing yesterday, and so they will split a little bit, and so you'll have a two-level system like this. Okay, all right. So good. So this is the sort of one-dimensional topological superconductor. Okay. So Shivaji introduced this Kitaev model yesterday, and so what I thought I would do is sort of show it to you again, sort of from the perspective of the way I was describing topological band structures before. Okay, and so Kitaev introduced this very simple and beautiful model of a one-dimensional P-wave superconductor, which you can basically think of as a chain of a one-dimensional chain of sites which have a hopping term on it, and then and there's a chemical potential term which sets where the Fermi energy is, and then there is a pairing term which adds a Cooper pair to a neighboring pair of sites. Okay, and so this is spinless electrons on a one-dimensional lattice, and since the electrons are fermions, this pairing term is necessarily a p-wave pairing term. Okay, and so given this Hamiltonian,
Since there's no conserved quantity, what is n?
What is
You have h minus mu n on the left.
h minus mu
First
n?
line on the left.
Yeah,
You've written h minus mu n.
it's this.
Oh, okay. So even though it's not a conserved quantity for that Hamiltonian.
Right, but it's n. Yeah. So C dagger C is that's an operator. I mean that's n. Yeah. So right. So this Hamiltonian, okay, I can write as a matrix like this, and if I do it as a function of k, then I have a Hamiltonian which is just like the Hamiltonian for an insulator, a one-dimensional insulator, okay, and it's a 2x2 matrix. Okay, and so this 2x2 matrix, the sort of non-superconducting part of it is on the diagonal, and it's just the one-dimensional tight binding model with a chemical potential, and then multiplied by tau z, which is h and minus h on the diagonal. Okay, and then the off-diagonal term is going to be this superconducting term, which gives you a sine k. Okay, and so I can think of this as so this looks just like so since it's a 2x2 matrix, I can do the same game that I had before, which is that I can think of it as a vector dotted into the Pauli matrix. Okay, and then and so you can see that this this D vector lives in the xz plane. Okay, and so it looks kind of like what we had before, okay, in the Schrieffer-Heeger model. So there are two phases. So if mu is very large, then dz never gets to zero, and so it's sort of a trivial phase, if you will. If dz is very small, if mu is very small, then you can see this D vector wraps all the way around. Okay, so in fact, these two phases are the trivial and topological phases of this one-dimensional superconductor. So this model is almost the same as this Schrieffer-Heeger model. It's a little bit different in the sense that so in the Schrieffer-Heeger model we had this symmetry where the Hamiltonian anti-commutes with sigma z. Okay, so this one we have the symmetry is different. It's this anti-unitary particle hole symmetry, and the constraint that gives you on this d vector is a little bit. It relates d and minus d. Okay, and this fact again guarantees that this Berry phase going around is either 0 or pi. Okay, and so the